Okay, now we're going to test a claim about a mean where sigma is unknown. All right, so the objective, once again, is to test a claim about a mean when sigma is unknown. And here's some of the notation we're going to be using. Of course, we recognize our sample size n, and then x bar is the sample mean. And then we have here mu of x bar, which is the population mean, but this is actually the mean of the sample means. This is from a sampling distribution, so we have the subscript. This is the mean of the sample means. All right, now there are some requirements. Three requirements. The first requirement is, as always, that the sample is a simple random sample. The second requirement is not really a requirement, it's actually a relaxing of a requirement. If you remember, when in the last section, we were testing claims about mean with the standard deviation sigma known. Now they're just saying that this is a method that we can use when sigma is unknown. So that's not necessarily a requirement. But number three, either or both of these conditions is satisfied. Either we have a normally distributed um, population, or we have a sample size large enough, and by large enough we mean greater than 30. If all these requirements are met, then we have this t statistic, this t test statistic that we can use. So this is the distinction between the last section and this section, is that in this section we're using a t test statistic, and in the last section we used a z test statistic. Now, um, the p-values are going to be found by either using table A3, which is the t distribution with n minus 1 degrees of freedom, or we can use the TI-83 calculator. And I think we're going to opt to use the TI-83 calculator, okay? All right, so let's take a look at two examples here. The first example I want to look at, here we have hypothesis testing, and it says assume that a simple random sample has been selected. So we have the first requirement from a normally distributed population. So we also have the third requirement, regardless of sample size. And test the given claim. Unless specified by your instructor, use the traditional method or the p-value method. Okay, we're going to be using the p-value method. And if the null hypothesis or sorry, identify the null and alternative hypothesis, the test statistic, the p-value, and critical values, and state the final conclusion that addresses the original claim. All right, now since we're using the p-value method, there's no need for us to find critical values. Critical values are only used when you are doing the traditional method. We're just going to compare our p-value to alpha. All right, so let's go ahead and do number 22. Number 22, a simple random sample of 40 recorded speeds, so I have 40 as my sample size, is obtained from cars traveling on a section of Highway 405 in Los Angeles. The sample has a the sample has a mean of 68.4 miles per hour. So that's the mean. That's the sample mean, that's x bar. And the standard deviation of 5.7. Notice they're still referring to the sample. So this 5.7 is not the population standard deviation sigma, but the sample standard deviation s. It says use a 0.05 significance level to test the claim that the mean speed of all cars is greater than the posted 65 miles per hour. Okay, so what we're going to do here is we're going to identify everything, and then we're going to put all this information into the TI-83, all right? So let's see. The first thing I want to do is I want to identify all the given numbers. So I see that n, the sample size is 40. That was given. I see x bar, the sample mean, is given to be 68.4. 68.4. Let's see, we said this sample standard deviation is equal to 5.7. What else do we have here? And use alpha, a significance level of 0.05. Okay, so we have all that information. Now we can actually go ahead and set up our null and alternative hypothesis based on the claim. Now here's the claim. We're going to test the claim that the mean speed of all cars. So making a test about, we're doing a test about mean. So we're going to use mu. The test is of the claim that the mean speed of all cars is greater than the posted limit of 65. So we're making a claim that the mean speed is greater than 65. That's the claim. All right. Now, once we have the claim, the next step is to identify whether the claim is the null or alternative. And in this case, since the claim does not contain equality, we know that this claim is the alternative hypothesis. And the null hypothesis is always the hypothesis that the parameter is equal to whatever the hypothesized number is. So this is our null and alternative hypothesis. These are them. All right, now that we have all that information, we can actually go and put it into our TI-83, and that will allow us to get the test statistic and p-value and all that other information. So let's bring in our TI. All right, so turn it on, and it says, using the TI-83 or 84, press stat. So we go to stat, we go over to tests, we go over to tests, and the test that we're doing now is a t-test. So that's number 2 here, number 2. So I hit number 2 for the t-test, and it asks me if I have data or statistic. I want to highlight that I have statistic and press enter, and then it's going to ask me for the statistics. The first one it asks me for is mu, and mu from the null hypothesis is 65. So we type in 65. Then it asks me for x bar. Well, x bar we found to be 68.4. 68.4. Then it asked me for x bar. What happened there? Let's go back up to x bar. We said that was 68.4. And the standard deviation, let's go down. The standard deviation, it says is 5.7. And then n it asks for, n is 40. So I enter all that information. The last thing it asks me for is my alternative hypothesis. In the alternative hypothesis, we have greater than. So I'm going to put that my alternative hypothesis is greater than. So I'm going to go over, select greater than, press enter, and then I go down and I calculate. When I calculate, it comes back with all the numbers that I'm asking for. Well, mu is greater than 65. That's the alternative hypothesis. That's all. That's the information I already know. This t is actually my test statistic. My test statistic is 3.77. So one of the things they asked me for in the directions was the test statistic. The test statistic. So our test statistic we found to be 3.77. So let's label that here. We have that our test statistic, that test statistic is a t, and it's equal to 3.77. So we have a test statistic, a t, which is 3.77. All right, let's see, what else do we have? It also asks us for the p-value. Well, the p-value here is given in scientific notation. Oops, calculator went off. It's given in scientific notation. The p-value is actually 2.68 or 2.69 times 10 to the negative fourth power, which is actually 0.0003 if you round it. So that is our p-value. Our p-value is equal to 0.0003. So that's one of the other things they asked us for is the p-value. So they asked us, let's see, we were asked, let's see if we've answered all the questions here. We were asked for the p-value, the null and alternative hypothesis, the test statistic. I said we don't have to find a critical value. Now we want to state the final conclusion so that it addresses the original claim. All right, now, because of the fact that our p-value is less than our value of alpha, so we're going to actually state our initial conclusion here. Because the p-value is less than alpha, so p-value of 0.003 0003 is less than our value of alpha, which is 0.05 for the significance level, we reject the null hypothesis. Reject the null hypothesis. Now, what that means is since we're rejecting the null hypothesis here, we're saying the null hypothesis is not true, we actually have enough information to support our claim. So our final conclusion would be that there is enough sample evidence to support the claim that the mean speed of all cars is greater than the posted speed limit of 65 on Highway 405 in Los Angeles. All right, so let's take a look at the next example, number 54, and it's about the height of supermodels. It says the heights are measured for a simple random sample, so the first requirement is there, of supermodels: Crawford, Buchan, Estova, Christensen, Hume, Moss, Campbell, Schiffer, and Taylor. They have a mean height of 70 inches and a standard deviation of 1.5 inches. So for these, let's see, how many are there? We have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 supermodels. That's a small sample, but it doesn't matter um, because we learned earlier that the mean height of all women was normally distributed, and we even had the mean and standard deviation. And actually, uh, it's going to say so here in the problem also. So anyway, these 9 supermodels have a mean height of 70 inches. This is not the mean for all women. This is only the mean for these 9 supermodels. And their standard deviation for these 9 supermodels is 1.5. So there we have X bar, and we also have S. They want us to use a 0.01 significance level. So that's our alpha. To test the claim, now here's a claim, that supermodels have a height with a mean that is greater than the mean height of 63.6 inches for women in the general population. Given that there are 9 heights represented, can we really conclude that the supermodels are taller than the typical woman? All right, so let's see. What we need to do is we need to go ahead here and we need to find our, we need to label all these numbers. So the first one is X bar, that's the 70 that's given. So X bar is the sample mean. We also have a sample standard deviation S of 1.5, and we have alpha. Alpha is equal to 0.01. So we have those numbers. Let's see what else we have. We also have N is equal to 9. Now, we also have the claim here. We're testing the claim that the mean height of supermodels is greater than the mean height of the general population of women. So our claim is that the mean height, the population mean for all supermodels is greater than 63.6. Once again, this is our alternative hypothesis, does not contain equality. The null hypothesis is then that supermodels have a mean height that is equal to the height of the general population. So this is saying that supermodels are not taller than the average woman. All right, so our claim is actually the alternative hypothesis. So let's go ahead and put all this information into our trusty TI-83 calculator. Alright, so let's see. Once again, what we're doing, let's turn it on first and clear out the information. We're going to stats, we're going over to tests again, and once again we're doing a t-test, because we don't know sigma, so we can't do a z-test. We go to t-test, it's already labeled statistics. Um, the mean from the null hypothesis is 63.6. 63.6. The mean from the sample, the mean of the supermodels was 70 inches. The standard deviation was 1.5, not much variation amongst their heights there. And the sample size was 9. Now, next we want to look at the alternative hypothesis. The alternative hypothesis here once again is greater than, so we highlight greater than. And then we go to calculate. And here's giving me my t-test statistic is 12.8. And the p-value is very, very small. The p-value is 6.5 times 10 to the negative 7th power. That's a decimal point, 6 zeros, and then a 7. So that's a very, very, very small number. So let's see. The test statistic then. Let's identify the test statistic. The test statistic, test stat. The test statistic was that t-score that we saw. And the t-score, the test statistic is 12.8. So the t-statistic is that, or the test statistic is a t-score and it's equal to 12.8. That literally means that this sample is 12.8 standard deviations from the average. And let's see, we have also the p-value, which we said was 0.60, a decimal point, 6 zeros, and then the number 7. So the p-value is 0.12345 6 and then a 7, which is a very small p-value. That's less than alpha, definitely. So once again, we reject the null hypothesis. So we reject the null hypothesis. And because we're rejecting the null hypothesis, we're actually doing it in favor of the claim. We're rejecting this hypothesis, which means the other hypothesis is probably true. So there is sample evidence to support the claim that the mean height of supermodels is greater than the mean height of the average, the general population of women.